Hello, everyone, and welcome to today's webinar. My name is Tipiso Morabe, and I am the Marketing Assistant at EIT South Africa. Today's webinar seems to be very, very good to begin off. We have strong numbers, and I do see a couple of our students in the chat box, a former student ambassador of the Engineering Institute of Technology, and some current students, and of course, some alumni. So basically, the webinar is starting as of this moment, and the first order of business would be the notification and sound slide. So this is just to make sure that you're able to turn off any notifications that might come through during the webinar. You'll be able to turn them on once we have concluded with the webinar, so you don't have to worry about any disturbances that might occur during your viewing or the presentation itself. Okay, some common questions or frequently asked questions. Ladies and gentlemen, please note that you will receive a recording as well as the PDF slides to this particular webinar. They will be sent to your email, the email addresses that you used when you were registering for this webinar. They'll be sent to you by the marketing team within the next 24 to 48 hours. Please make sure to monitor both your junk, spam, and promotional folders. If you do not find them in your mailbox, they should land there or they should come through as normal. Now, for the certificates of attendance, as this is a technical topic, you will receive a certificate of attendance. However, you will need to request it, and this is done through you completing just a short survey, and then you input your details so that we have them to put on the certificate. Please note that the process is automated, so please put in your names and surnames as you would like them to appear on the certificate. Also, make sure that your email addresses are correct so that you do get your certificates. Please note again that the certificate form will expire. They normally do on Monday, the following Monday, that is at 5 a.m. UTC time. So please make sure you request for the certificates. Then I will provide a QR code as well as the link to request for the certificate once the presentation has concluded. Now, if you're new here, let me tell you a little bit more about EIT. We are an engineering specialist. We offer engineering programs from a professional certificate to a Doctor of Engineering program. These programs can be studied either online or on campus, depending on which program you choose to study. We have industry-orientated programs, meaning that we really do take note of what is going on in the engineering fields and the trends that they follow, and we implement these into the programs that we develop and offer at the institution. We are a world-class accredited Australian education provider, and we are recognized by the Australian government. Some of our courses actually have international recognition under the Dublin Accord, the Sydney Accord, as well as the Washington Accord. So our lectures are actually industry experience. These are people who've actually worked in the engineering field and are now teaching and are now sharing the knowledge that they have regarding engineering in the studies that they conduct at EIT, or the lecturing rather. And then lastly, we offer a unique delivery model. This means that our programs are offered both online and on campus. All our programs can be studied 100% online. And then for on campus, you can study either our bachelor's, our master's, as well as the Doctor of Engineering in our campuses. Currently, we have 3 campuses, one in Melbourne, Brisbane, as well as one in Perth, which is our head office. So discover why EIT is the institution that you should choose to study. These are all our accolades. So we have gotten first place for about 2 awards, and then we have been top 3 for another 2. And then quite recently, we've just won the 2024 West Australian Export Award for International Education and Training. We actually won the award as well in 2021. So you are sure to know that we do really have valuable information that you would like to know and like to learn in the engineering field. No, today's topic is going to be the challenge of water security in arid economies, and this will be presented by Dr. Anthony Turton. He is an EIT lecturer and as well as head of strategy at Nexus Resilience. Dr. Anthony, this is it from me for this portion of the webinar. Good luck. I think it's going to be a brilliant one. We have some lovely numbers for you today. I will see everyone once the presentation has concluded for the post Q&A session, as well as for the certificate link and QR code. Please leave any questions you have regarding the webinar, as well as the presentation in the Q&A box or the chat box, and I'll be sure to answer any incoming questions for today. Thank you so much, everyone. Dr. Anthony, you can go ahead.
Thank you very much. Where do I take control?
So top left screen, there is a, yes, right next to the time, straight across. Okay, there's Lily.
Okay, must I talk to the slide? Okay, right. Good day to all of you people. I thank you very much for taking the time and effort to log in. It's my privilege to talk to you today. I'm a South African, but I've got an international footprint. I've worked in various parts of the world, and one of the roles that I played was within the World Water Council, where I still serve to this day as the editor of the official journal Water Policy. So I'm more of a water policy expert, but of course this links in directly with engineering and with engineering trends and changes over time. So my core strategy, my core knowledge is actually of water as a national security risk, and this is something that is not usually available, but this is one of my core offerings. And of course, I've got a specialist knowledge over a couple of decades, in fact, of acid mine drainage in both the coal and the gold fields of South Africa, and I'm now starting to expand that into Australia. I now live in Perth, Australia, and I'm quite interested to compare Australia with Southern Africa, where I've also got a lot of interest. But of course, I'm now working in the Middle East, North Africa area, and there are lots of interesting things happening there. So that's my introduction. So let's start. Where are we now? Okay, we got to start. No, not happening here. What is happening here? I need to. No, this is not happening for me. So what do I? Okay, I'll click on there. Okay, right. Okay, sorry, these technical glitches. My apologies. Okay, so we've got to start by defining the problem. The way we define the problem actually pre-selects the solution, and that's an important point of departure to note, because problems are defined typically in the context of what we call a paradigm. So paradigms are things that order logic, and they pre-select the solutions that we're thinking about. The prevailing paradigm in the water sector at global level is one of water scarcity. So anywhere in the world, wherever you go, generally, particularly in arid economies, people talk about water scarcity. What is the water scarcity situation? How do we manage water scarcity? And I'm of the opinion that this is part of our problem, and we'll expand on it as we go through this talk. I don't believe it's water scarcity. I believe it's another problem. So thinking in terms of a paradigm of scarcity, in my professional opinion, is part of the problem. Why? Because if we're thinking about scarcity, we immediately start thinking about how do we mobilize more supply? What do we do to increase the security of supply? And I'll expand on that later on in the conversation. Therefore, I think we need to have a new paradigm, and this is let's say that this is my personal professional objective at this stage in my career. Wherever I go, I talk about this new paradigm, and that new paradigm, I think, is something that we have to start thinking about. We have to start getting our heads around, and in particular, we have to start training young professionals to start thinking about this new paradigm, because they are going to engage the rest of their professional life within that new paradigm. So in my view, in my opinion, a lot of the engineers, particularly the older ones, have grown up in this paradigm of scarcity. But there's going to be a new paradigm change in the not too distant future. It's already happening, and I believe it's happening in particularly in water security area of arid economies. Note, I've already begun to shift the paradigm by framing it in terms of 3 specific factors. So this is where we start the conversation now. I've been talking about water security, whatever that means, and we will go into what water security means as we progress. But I've also been talking about aridity. What does aridity actually mean? And we're going to be talking about the economy. So think about these things, because typically engineering students don't think about things like the economy. They don't think about the biophysical drivers of what aridity is about, what causes aridity. They just think about the solutions to those problems. So this is part of the thing. Now we get to a challenging time now, because I'm always terrified when I have to embed something in a presentation, and I'm going to have full confidence in the technical team we have here, and I'm going to click on this. Let's see now. Okay.
Okay. Dr. Anthony, would you mind just telling me which slide are you on, and then I can move the presentation on for you, and then you can just present. I don't mind moving through the slides.
Okay. Can you click that, get that hot link going for me there, please, Seth?
Okay. Tell me what slide you're on right now, and then I can move the slides for you.
I'm on slide 9 of 31.
No problem. And then you can tell me to move the slides as you progress through your presentation there.
Okay. So she's got to do it now. Must I click that?
YouTube link on that slide of 9.
Okay, I will move the slides for you, Dr. Anthony. No worries. Just tell me once you're ready to move.
Okay, now I want that hot link to Gibbs, Gordon Institute of Business Science. There's that video link.
Okay, there we are. Under the topic, not the topic, the heading is defining the problem, correct? The heading, rather.
The hot link is.
Yes, you are on the correct slide, Dr. Anthony.
What must I click on that link?
Do you want to click on the, do you want to play the video?
I want to
yes,
activate
please
it,
do.
Okay, right. My apologies for this delay. She's asking. I'm always concerned about these hot links. They never work for me. Okay, look, if this hot link doesn't work, I'm going to just bypass it.
I have played the presentation. Are you able to see it, Dr. Anthony?
I can see nothing now. Have you played it, or is it playing?
It's playing. Let me just share my screen, and then I will play it for you. No worries.
Okay, thank you. I can see nothing on a shared screen.
Dr. Anthony, I'm just going to share the link for the people for the presentation, or rather the YouTube link in the chat box, and then they'll be able to watch it once we have concluded with the presentation. We'll also be sure to share it in the email that will go out so that they have access to it once the presentation is done. Will that suffice?
Hi, Teppy. I think what we'll do for now is we'll just share the slides back on, and Anthony will take control and
There we
continue
are.
with his slides. This is Lily here.
Yeah, I can hear you, Lily. I don't think you guys heard me previously. I was saying what we can do is actually provide the link to the YouTube video on email once we send out the EDM, and now everyone can have access to it once the
Yep.
presentation is concluded. Will that
No
suffice?
worries. Yep. So we'll just share out the screen. Sorry, the link, and then we'll just continue the presentation. Yep.
Okay, I've taken control of the screen. I've reshared the
Yep.
presentation, and we are on slide 9 as we previously were. So can you guys see slide 9?
Yep, we can see slide 9.
Okay, no problem. And then Dr. Anthony can just tell me to move through the presentation once he is moving through.
Also, can we take control of the presentation?
Please
and
do.
flick through the slides?
Of
Yep. So we're
course.
taking control now. And when we flick through here,
Yeah, I can see
can
that.
everyone see that one?
Yeah, it's defining the problem that is up on the screen, which is slide 9 of 31.
Lovely. So I'll give the headset back to Anthony now.
That would be great. Thank you, Lily.
Okay, so I have no idea what to do, but okay. Okay, so I'm not going to click that. Okay, right. Okay, I apologize for that technical problem. That's one of the reasons why I'm always concerned about putting hot links in PowerPoint presentations. I thought it would be different this time. Okay, so let's start to define the core problem now. I mentioned about the fact that in that video link that didn't play, I talk about the crisis in the water sector. And I use South Africa as a reference, and I say specifically that in my professional opinion, we don't have a crisis of water, we have a crisis of critical thinking. And the case that I make is that water is a flux that moves in time and space. Therefore, it's an infinitely renewable source, but we manage it as a stock that is a single-use item that we take, we make waste with, and we discard it, never to be reused again. So this idea of the crisis of critical thinking, that's what I'm talking about in the rest of this lecture today. So we're now drilling into what this crisis of critical thinking is. And we're going to start now by defining the problem. Can I make this full screen? Because
Yes, Dr. Anthony?
yeah, okay. I'm going to make this thing full screen because I'm looking into little tiny screens here. Okay, okay. So if this map that we see now is a map of water stress, and water stress is an interesting concept. I'm going to expand on that concept now as we go through this lecture. Water stress is going to be experienced by every single person that is listening to this lecture at the moment in their lifetime, and it's going to become more acute. And if you look at that map in particular, you'll see there are different colors, and black being the worst color, black for extremely highly stressed economies, and the softer colors, the blue colors, are the less stressed countries. Now, immediately you start seeing a couple of interesting things here. The first thing that you start seeing now is that the extremely high water stress areas are typically the Middle East, North Africa, India, and also Southern Africa. So this got me interested when I saw this first in the early 2000s. At that stage, I was working on water as a national security risk in South Africa, and I started to ask myself the question: has anyone in South Africa or Southern Africa realized the extent of the water stress that's coming in the future in their lifetimes? But if you look further now, you start seeing other interesting phenomena. So I'm currently talking to you from Australia, and you'll see that Australia's got high water stress, but Australia is very similar to other parts of the world. So let's expand on that now. So economic growth in the Middle East and North Africa is fundamentally constrained by water. I mentioned earlier on that I'm doing a lot of work in the Middle East at the moment now. Middle East is an oil-based economy that's constrained by water. And that's no different to Australia. That's, for example, a minerals-based economy constrained by water. So there's similarities if you think about this thing differently. So Southern Africa is rapidly approaching MENA status. MENA is the Middle East, North Africa status. And this is something that's quite alarming for the average water resource professional because they don't look into the future, or they tend not to look into the future. Australia is better off, but will increasingly face finite limitations to its economic growth potential, and will resemble countries like Peru, Mexico, Niger, Turkey, Pakistan, Turkmenistan, Uzbekistan, Kurdistan, and Mongolia. And now this is the kicker: if nothing is done. So if nothing is done, that's what it's going to look like in 2050. And the good news is, because we are smart people, because we've got very, very cutting edge engineering, science and technology capabilities in different parts of the world, we can do something about that. So this is actually a good news story. It's not a bad news story. Stated simply, water is an economic enabler. So how we manage or change our thinking about it will determine our economic future. Now we look at Australia, for example, minerals-based economy, current trade wars going on, uncertain future, water resource availability is changing. This is no different to Southern Africa. So I would like to see a greater parallel or greater linkage between Australia and Southern Africa in the near future, because the experiences and the technical aspects are very similar. And here I introduce a term that I'm going to expand on a little bit further: the notion of a second order resource. A first order resource is a natural resource like oil, like water. That's a first order resource. You either have a lot of it or you don't have enough of it. But a second order resource is what you do about your changing first order resource availability. And I'll expand on that now as we go through. So at this point in time, I would like to introduce the concept of hydraulic density of population, because that water scarcity map that we saw is all about the hydraulic density of population. And what does a hydraulic density of population mean? It means the number of people per flow unit, and we can now compare apples to apples in different parts of the world. It was conceptualized by a colleague of mine named Malin Falkenmark, a professor in Sweden. She was deeply involved in the negotiation for what became known as the Dublin Principles, and that was all part of the World Summit on Sustainable Development. The so-called Rio Earth Summit. He asked one simple question: is there a finite limit to the number of people that a given unit of water can sustain? And believe it or not, up until that point in time, nobody had actually answered that question. So this sent her down a very interesting rabbit hole, and she became quite famous, world famous, in fact, on this. And she said, let's compare every country in the world. Let's take as a conceptual unit, what she called a flow unit of 1 million cubic meters of water per annum, and see how many people there are that depend on that particular unit of water, that flow unit of water. Now you can compare countries to countries, regions to regions, and you start getting an interesting thing now. She's also started looking at what it means to survive, and she created a thing called this water barrier. And she said that as we approach the water barrier, which is a fundamental constraint to economic development, it also opens up another can of worms. It opens up issues of social stability, loss of investor confidence, and all kinds of other issues that are typically out of the realm of scope of work for a normal engineering consultant, but something that we have to understand. So we can think of water as a first order resource, as I said earlier on. But there's limited empirical evidence that social stability is possible once the water barrier is crossed. Now that starts to become very interesting, because we talk here about empirical evidence, very limited empirical evidence that social stability is possible once the water barrier is crossed. But it's not impossible. It can be done, and the empirical example for that is, in fact, the state of Israel, believe it or not, where they've long ago approached the water barrier, and they are capable of surviving beyond that because of their technology, because of their reuse of water, because of the way they think about water. So the exception could be, well, it is currently Israel, but it could also be Australia, because they've got very similar problems. There are, of course, fundamental differences. Israel is a very small country geographically. Australia is a massive country, massive country. It's just West Australia, where I am now, is the size of South Africa and Namibia combined, and it's only got a population of 3 million people in it. So that's one of the reasons why it's not as water stressed as it should be. The critical variable is the capacity of society to innovate as the water barriers approached. And when I'm talking to EIT now, we're talking about trying to develop concepts and tools to help engineers to start understanding what happens when we approach that water barrier, so that we can continue to provide solutions beyond the water barrier. And this is where we get into a thing called social adaptive capacity. The capacity of a society to adapt to fundamental changes in their water availability. This is a second order resource of great value. South Africa has had a very high level of social adaptive capacity. It is currently dwindling for a number of reasons. We won't go into that now, but just think of a social adaptive capacity, or the capacity of a society to adapt to changes in water resource availability as a resource in and of itself. So if it's a resource, if social adaptive capacity is a resource, how do we create it? How do we culture it? How do we grow it? How do we nurture it? And this is where we've got to start moving the engineering professions, the engineering professionals, if we're thinking about the future. So we're talking now about the hydraulic density of population. And that photograph is a very interesting one, because that photograph was taken in the Royal Swedish Academy of Sciences when Malin Falkenmark was given a Lifetime Achievement Award. And that's her sitting in the middle with that pink colored jersey on, with jacket on, and that's me with a tie sitting on her left, on the right, if you look at it from the viewer's perspective. And what's interesting about that is that her work is now globally cited as the foundation for water stress. But when I was invited to this particular event, I used this event because I was asked, all of those people that you see in those photographs were invited to that particular event as part of her Lifetime Achievement Award, and they all gave a paper. They all presented their own work, and that was published, one of the first papers that I've ever seen that talks about the Anthropocene and the transition to the Anthropocene from a water resource management perspective. That came out of this particular event. But she came to the conclusion that as one approaches what she called a water barrier, and you transition into what is known as absolute water scarcity, society becomes unavailable. Society becomes unstable for a variety of reasons. And of course, we don't want unstable societies, because that creates a whole lot of other second order problems, and we want to avoid that. One of those is the social license to operate. And this is happening very much in Australia at the moment, where we've got a massive mining economy that's growing rapidly, but it's growing in very arid areas. And those very arid areas are also the home to Aboriginal populations. And the law is changing now to support Aboriginal rights, so-called First Nation rights. And this First Nation right is an extremely important issue. In fact, if mismanaged, can become a major risk to mining investment and mining infrastructure development. So the social license to operate, it becomes increasingly important as we approach that transition, that water barrier into absolute water scarcity. And this is where it now becomes an engineering problem. The financial risk and the reputational risk to your mining companies and indeed to your governments starts becoming an engineering problem, and that's what we're going to talk about for the rest of this engagement. So this image here shows, as I say, the Royal Swedish Academy of Sciences. I was very humbled because when Marlon was given her Lifetime Achievement Award, they also said that she could invite 10 people from anywhere in the world that had used her work and taken to the next level. And I'd use her work in my PhD study. In fact, I used her work in my own work in the South African Secret Service at that point in time, where I was developing the model of water as a national security risk. I became the first person in the intelligence community looking at water as a national security risk. And that was based to a large extent on her technical work about this absolute water scarcity and the water barrier. This has now been adapted to ASX companies. So this is Australian listed companies, Australian Stock Exchange listed companies in the Witwatersrand goldfields and in Mpumalanga coalfields, where I've acted as a strategic advisor to senior decision-making executives of Australian companies operating in South Africa, facing this very risk. So let's now drill into what aridity means. And this is an important conceptual thing for the listener to understand. So here we've got a simple hand drawing. We've got three different regions. We've got, if you look at the top, we've got Scandinavia, we've got Southern Europe, and we've got an African country, Zambia. And what's interesting about each of those is they've each got 1,000 millimeters per annum of rain. So they've got the similar amount of precipitation per annum, 1,000 millimeters per annum. But if you look at the next line, the evaporative demand differs fundamentally. So Scandinavia, the loss of water to the evaporative demand, or loss of water to the atmosphere, is 500 millimeters per annum. In Europe, in Southern Europe, it's 1,000. And in Zambia, it's 1,500. So if we now look at the next line, if we think of an imaginary tank of water that is 2 meters high, and let's assume that we start off at the beginning of a 2-year cycle, we start off with that tank half full. Now we're only going to fill up that tank with water from precipitation. So and we're going to subtract from that the water that we lose to evaporation. So in the case of Scandinavia, the tank starts at half full, so it's 1 meter high water, but after a year it becomes 2 meters high because you get an additional 1,000 millimeters of rain and you lose 500. So in other words, that's what the tank looks like in Scandinavia compared to the central one in Southern Europe. You get an additional 1,000 millimeters of rain, you lose 1,000 millimeters to evaporation, so your tank remains as it was at the start of the cycle. But now look at Zambia, and this could be Australia, it could be any other arid part of the world, because your precipitation is smaller than evaporative demand, your tank at the end of the first year is now only a quarter full. And after 2 years, we see a stark difference. After 2 years, we see in the case of Scandinavia, the tank overflows with water. In the middle, Southern Europe, you see it's remained stable. So even though it's arid, it's stable. But in the Zambian, and let's call it the arid part of the world model, even though you've had 1,000 millimeters of rain, you've now got an empty water tank. So this helps us to understand that it's not about a shortage of water, and that's what that video clip that didn't play, that's what that's all about. It's not about an actual shortage of water. Aridity is the result of evaporative losses exceeding precipitation in each geographical domain. So it's all about managing evaporative losses. How do we manage losses to evaporation? And we can then start getting into all kinds of interesting things about multipliers that we can start creating if we manage evaporative losses. So it's about finding the multipliers that are embedded in the current hydrological cycle rather than mobilizing the resource in the first place. And this is where I would like our thinking to start shifting. Our core engineering challenge is to solve the many complex problems defined by the MAP-MAR ratio. MAP is mean annual precipitation, MAR is the mean annual runoff. So the ratio of MAP to MAR, which is illustrated in that right-hand diagram there. MAP, mean annual precipitation, MAR, mean annual runoff. How is that different? Let's look at the numbers now. So these are the numbers just at a very generalized level globally. And the first thing that you'll notice is, for example, Asia has got an exceptionally high level of rainfall. It gets much more than other parts of the world. Compare that to Australia. But you'll start seeing a couple of interesting things here now. The MAP-MAR challenge. In Africa, at continental level, 80% of the precipitation is lost to evapotranspiration. 80%. So of 100 units of rain falling out of the sky in Africa, only 20 end up in the river. Now, that's, of course, Africa is a big place, and we've got extremes. We've got the Congo in the middle of the continent, which is very high rainfall, 4,000-5,000 millimeters of rain per year. And then we've got the Kalahari in the Sahara Desert in the north, Kalahari and Namib in the south, where you've got like 10 or maybe 30 millimeters of rain if you're lucky. So that's an average thing. But let's just look at this in greater detail now. In Australia, it's 65% conversion, ratio between MAP and MAR. Water security will increasingly be about unlocking the multipliers by using a unit of water multiple times. And this I see is very much the future of water resource management. And this is where I see the future of hard engineering, hard hydraulic engineering, increasingly being integrated with computer modeling, with smart technologies, with Internet of Things kind of thinking, with predictive artificial intelligence. A growing range of engineering problems will cluster around the following. How do we minimize evaporative losses? That's the first thing. And that is a very complex engineering challenge. How do we minimize evaporative losses? Think of a large dam. Think of the massive amount of evaporation that's taking place off that large dam. How do we minimize that? And we'll talk a little bit about that now. But the second thing is how do we unlock multipliers? So if we take the African sort of continental average of the 100 units of rain that fall out of the sky, only 20 units end up in the river. So there's a multiplier at work there. If we can store water in a way that it's not being lost to evaporation, there's a multiplier. How do we measure that? How do we build systems, engineered systems, IT systems, technological systems? How do we build those systems in a way that can measure and monitor the efficiencies and the multipliers that can come out of the elimination or the reduction of evaporative losses? And I think this is an important thing. And of course, the final thing that I think is, in my professional opinion, one of the absolute holy grail of water management, water resource management in the future is going to be the reduction the elimination and the processing of brine. I mentioned I work in the Middle East. Middle East got massive amounts of desalination. Desalination sustains the economy, but they produce huge amount of brine. So how do we reduce that brine? How do we convert that brine into a business model that can now be mined? For specific minerals, for example. How do we change our fundamental thinking about the way we manage brine? And of course, what I forgot to mention here is supporting the social license to operate. We had a case here in Western Australia, up in the Pilbara area, where a major mining company was in huge amount of trouble for an Aboriginal rights violation that cost them very, very dearly. There were court cases against it. I'm not going to go into details, but literally they almost lost their social license to mine, and the courts are coming back very strongly now in favor of Aboriginal rights, and therefore literally a mining operation or mining company can lose its social license to operate, which now translates immediately into a commercial investment risk that needs to be managed. So that's the sort of the string of logic that we need to start thinking about. Right, I mentioned that I was involved in the early 2000s in developing a model for water as a national security risk. This is only one part of it. It's a very complicated model, and this is only a very, very rudimentary rendition of that. But if you think of water availability and water shortage as translating into water as a national security risk, it takes you into a completely different domain. And most engineers haven't thought of it in this way. So let me just introduce this to you in a very, very simplified way. This is a model that was developed, as I say, and it introduces a couple of concepts. So let's just think on the conceptually now of new ideas, and one of those new ideas is a thing called a threshold of concern. What is the threshold of concern as we approach certain barriers, certain transitions, where certain pivotal moments, certain pivotal events, and we'll define some of those now in the model. But the second thing is, on the vertical axis, we talk about volume, and we can think of volume as Q1, Q2, and Q3, and that's the volume of water that we have available at any moment in time. And on the horizontal axis, we've got time, T1, T2, T3, etc. So we start off at a moment in historic time when you've got a certain amount of water that's available, that's your natural supply, Q1, and it intersects with a moment in time, T1, when you start developing your water resources for economic development, and you start developing the economy through the development of of your infrastructure for water resource delivery, and you start going to more and more sophisticated infrastructure over time, until you reach the point Q2, where you start exceeding the amount, demand starts exceeding the amount of available supply, and infrastructure is increasingly under pressure, can no longer deliver it. So you then go into this thing beyond the normal sort of sphere of hard engineering. We start thinking now about adaptation. How do we adapt? How does government policy, how does mining policy, how do investors thinking about adapting? And that's when we have to start making very, very hard choices. And those hard choices are shown in the top right-hand part of that graph there, about, are we going to continue on a pathway to prosperity, or are we going to continue? Do we have to realign our water availability with the aspirations of society, and are we going to cut back on supply? We see this happening in South Africa at the moment. The Rand water area of supply, the Gauteng area, is exactly in that upper right-hand part there now, where they are forced to throttle back for various reasons, because there's just not enough supply. Demand has exceeded supply. So the question now is, either you throttle back supply and you go down the austerity route, which has got all sorts of very complicated consequences. One of of them being a loss of investor confidence, a loss of jobs, increased social instability, all these unintended consequences of throttling back water supply? Or how do we manage under conditions of fundamental constraint, but by generating what is known as new water, and that's where the water recovery comes in. That's where the desalination comes in. That's where the recycling of water from waste, etc., etc. And that's very much the future, I think, of the engineering profession that we are talking about now. So that quadrant in the top right-hand corner there is one of great importance, and that's happening in Western Australia right now, that's happening in South Africa right now, and it's happening in other parts of the world as well right now. It's not only an Australian and an African thing. For example, it's happening right now in the state of California. It's happening in other parts of the world as well. The horizontal axis, I've mentioned that. Time, you start into time one to just developing your early water supplies, and your basic infrastructure, typically dams and pipelines and pump stations. And as the dams get bigger and as the pipelines get longer and the pumps get more sophisticated, you reach a point in time at T2 when you can no longer supply with dams and pumps and pipelines, and you now start having to make these hard choices. Do you continue to grow the economy or do you stagnate? And here in the Western Australian case, we've got the goldfields around Kalgoorlie, where there's some significant new finds in the Kalgoorlie area, significant new mineral finds, but it's fundamentally water constrained. And there's a pipeline. I'll show you the pipeline just now in one of the next slides, and the limitation of that pipeline. So it's all going to be illustrated here. So let's focus just in the top right-hand corner. The question now is, do we want a future of prosperity, or do we want a future of austerity? And now, where does engineering fit into that? And how do engineers start reframing their thinking about just developing supply to actually managing and developing solutions for bigger things such as social stability, investor confidence, etc.? So the point I want to make here is that each transition from T1 to T2 to T3, Q1, Q2, Q3, each of those transitions changes the level of complexity. So at the lower level, T1 and Q1, that's just purely about engineering. That's only engineering, nothing else matters. When you start getting to T2 and Q2, you now start talking about economics, you start talking about social stability, you start talking about national security, so you start talking about a whole lot of other alternative things. So your engineering teams have to understand how to speak the language of other professionals, and of course your clients, your governments, and your mining companies, they have to start changing the makeup of the technical teams that manage their concerns if they're going to manage it beyond the T2, Q2 kind of environment. So that's the point, is that each transition is about complexity. And the next concept I'd like to introduce is T1 to T3 is all about non-linearity. It's we don't see linear changes taking place. We see this exponentiality that starts kicking in, non-linearity that changes the mix of professionals, and that's an important thing. And of course, when we get to T3, that's about changing the paradigm. What I mentioned at the start of this conversation. How do we rethink our paradigm? And if you look at the bottom of this graph, I talk about hydraulic missions, and that's the South African one. In this case, where we've had a hydraulic mission, we've had 3 different hydraulic missions. We've actually had 2, but we are now in the 3rd one. And the first one is about getting more water. That's the paradigm of scarcity. But then there's the second, with the 3rd hydraulic mission, is about how do we create new water? How do we recycle water that's socially acceptable, economically viable, technologically possible? And that's the sort of mix now. Are members of society happy drinking recycled sewage water? Is it safe to drink recycled sewage water? What are the social barriers to that process? What are the technological barriers? The persistent chemicals, your forever chemicals, the recycling of pharmaceutical products from waste, etc., starts becoming the problem. So, where's Australia on this journey? let's rethink this thing in a different way now. I was working with another Swedish guy called Leif Olsson, who had an interesting background, and him and myself cooperated on working on this concept of a turning of a screw. We wanted to try and introduce the concept of non-linearity to the water resource professional community. And if you go back to the previous graph where the T1s, T2s, and T3s, I'm going to now represent on this linear arrow, this vertical linear arrow. So early supply before T1 is about early development. It's about your rudimentary, building a dam, building a weir, etc., etc. The second one, T2, is about economic growth. And it's interesting here in Perth, for example, because Perth is geographically a large city with a relatively low population density. So the pipelines are all very long, and the geographic footprint of the Water Utilities Corporation is very, very big. And so it starts getting to be rapidly more complex over time. And there's certain limitations to what they can do, as even though they're a world-class utilities corporation. So that economic growth, T2 becomes the big hot issue, and that's when we start going into this adaptation. And I think that's where Western Australia is now. That's certainly where South Africa is, and other parts of the world, as I mentioned earlier on. And then we start talking about sustainability. So each of these things is like the turning of a screw. And that if we don't get it right, we ultimately face ecological collapse, but we also face economic stagnation and social dislocation, which is not a good thing. So the water security model that I've developed for national security purposes is about non-linearity, non-linear transitions, and it helps the individual decision maker to start anticipating when barriers are going to be approached, or when certain threshold events are going to be negotiated, or how do you do things differently? How do you survive within a changing environment? We've got to limit the ecological impact, because one of the characteristics of these semi-arid areas is quite high level of ecological sensitivity, and I'll talk a bit about that in some of the future slides now. And the important thing now is team composition that changes over time, from a purely engineering team to eventually about the economics and policy people, and social people, and anthropology and legal people, and all that kind of stuff. So it's the whole idea of this cumulative ecological impact and the social and political fallout that happens over time, where the social license to operate becomes a critical risk, an increasingly big risk, as we see now in Western Australia. We've seen it in South Africa as well. Adaptation, at the end of the day, is about balances between the social license to operate and investor confidence that underpins the economy. Team composition over time will become more complex to mirror the environment, to mirror the real world problems that are being managed. So you start off with engineers, then you got environmental scientists, then you got a data scientist, and then ultimately social policy scientists, anthropologists, all that kind of stuff that eventually comes in. They all speak a different language. They've all got different perceptions of the world, and they've got completely different methodologies, and that's where it gets challenging. But innovation becomes a critical factor, and I believe that EIT is a place of great innovation, and that's one of my reasons for being interested in working with EIT, because I believe that innovation will become the driver of change, the driver of growth for the future. That's the difference. That's the second order resource that I'm talking about that will be needed to survive in the future. Okay, let's go back to the Royal Swedish Academy of Science now. And I mentioned earlier on in that video clip that didn't play that I believe we've got a crisis of critical thinking. We don't so much have a water crisis. We have more of a crisis about the way we think about water. And the interesting thing is that we live in a planet Earth, that is two-thirds covered with water. 2/3 of planet Earth is covered with water. In fact, salt water is 97% of the total volume of water on the Earth is seawater. Only 2.5% of that water that's available on planet Earth is fresh water, and of that, the majority is tied up in glaciers, etc. So we actually don't have a water problem. We have a salt problem. we have a solved problem. If we view water as a finite stock, then we are approaching the end of the road in arid economies for the simple reason that the cumulative ecological impacts is destroying the social license to operate and ultimately is going to bring the economy down. So this is the important thing. Water as a finite stock is a bad news story because we're reaching the end of the road. And if we continue to mobilize a diminishing volume of water, and we continue to pollute that diminishing volume of water and damage it with our persistent chemicals, etc., we are approaching literally an existential crisis for humanity. So we've got to avoid that. So the important thing I've mentioned here is that water is a flux. It moves in time and space. The volume of water we have on the planet is the same as we had when the dinosaurs roamed free. And in fact, I can guarantee you that when any one of you cleaned your teeth this morning, and I'm sure you all did, that the water that you put in your mouth went through a dinosaur's kidney 53 million years ago, and went through someone else's kidney maybe 24 hours ago, maybe a week ago. So in other words, we already recycle water, and we've got to just do it properly. We've got to think about water in a different way. If we think of water as a stock, that's the paradigm of scarcity, and it's a bad news outcome. But thinking of water as a flux is the paradigm of abundance. And the good news story is because it's a flux, it is literally infinitely renewable, which means that we don't have water constraints in our national economies. And that's the good news story that I want to start evangelizing, if we want to a better word. And the question here is Australia ready to embrace this paradigm of abundance? And I think we've got to start pushing the limits on this one now. So when I was thinking of this some years ago on this national security risk team that I was involved in, I was enamored by the infinity symbol. And that infinity symbol I put on a grid. I love grids. Think of the grid as 4 different systems, and we'll go into each of these systems now as we go as we expand this conversation. So if we think of a flux as an infinite flow, a closed loop flow, if we superimpose this grid onto that flow, and we'll start seeing that the left-hand side of this grid, the left hand is all about either state level of government, if you're in a federation like Australia, or national government, if you're in a place like South Africa, which is a unitary state. So national or state government works on the left-hand side of that grid, and your municipal or local government works on the right-hand side of the grid. So really there you see an interface between the two. And you start seeing that the top left is where it all starts. That's where precipitation happens. That's where rainfall falls out of the sky. And this number is changing globally. And we'll look at some numbers now. But that's the important part. That's where your ecological systems are, where the water comes into the system, into the loop as a point of origin. The bottom left is strategic storage, so dams, and we'll talk about different strategic storage now in this new paradigm of abundance, one of them being aquifer storage and recovery. And that's an important thing for the future. That's an important comparative advantage that I think Western Australia has, because they are quite deeply involved. In fact, they are cutting edge developments in that area. So strategic storage, getting back to what I said earlier on about the MAP-MAR conversion, the loss of evaporative or management of evaporative losses. Well, if you can store water in the ground, then you're managing those evaporative losses. The top right is where the economy happens. And the bottom right are all the return flows. So your municipal water, your water corporations, etc., they take water from the lower left to the upper right quadrant there, and they also have to manage return flows back into the ecosystem, typically sewage or wastewater return flows, which can be quite complicated chemistries, and they either flow back into the ocean or typically into rivers, etc. So how we think of this infinite loop, or how we rethink this infinite loop, will drive the way we're going to start asking new engineering questions in the future. So let's start looking at some home truths. This is Australia. It's got a range of precipitation. You see on the right-hand side, the scale there goes from extremely high, from sort of 2,000 to 3,000 millimeters of rain in certain parts around Tasmania and up in Queensland area. you've got very high levels of rainfall, but the majority of the country has got relatively low levels of rainfall. Look at those middle green colors there. The middle green color is between 400 and 600 millimeters. 400 and 600, that's what Namibia gets. So Namibia and Botswana are very similar to Australia, for example. So you also see this gradient that changes from north to south. And it also changes from east to west. The majority of Australia, in this case, has less than half of the global annual average of precipitation. So we can say that Australia, as a country, has got a fundamentally water-constrained economy, and that's an easy statement to make and to defend. But there's also a spatial disconnect between the areas of higher rainfall and economic activities. And I mentioned earlier on that model of mine, that national security model, where I mentioned T1, when you start developing your infrastructure. I will show you now what's happened in the case of Perth. Pipelines are very important. I wrote a chapter in a book some years ago called Precipitation, People, Pipelines and Power. And that explains how pipelines are used to straddle these isohyates. They used to straddle the economic development or enable economic development from areas that are either water abundant to transfer water to areas that are water scarce to enable economic activity to carry on. And as a result of that, political power and economic power flows. So precipitation, people, pipeline, power, those are the four important variables that we need to think about. And that's the Kalgoorlie pipeline. This is a pipeline that comes from a dam in Mundaring, in Perth here, a little bit north of Perth. I was there just about 2 weeks ago, and they've built a pipeline almost more than a century ago. They built that pipeline, a very, very long pipeline, 600-kilometer long pipeline. My son's worked on that pipeline as an engineer. I've driven along parts of that pipeline. It's an amazing piece of engineering, but it supplies water into the goldfields around Kalgoorlie. And if you just look there now, you can clearly see it takes water from an area that's relatively water abundant to an area that's relatively water scarce. And now there are all sorts of limitations to that, but where do we go from here? How do we continue to develop those goldfields with this fundamental water constraint? Larger cities in Australia are all associated with the better watered areas. And but the economy is driven by mining, and that's typically located in dry areas. So in the case of Australia, the mining is either in the goldfields in the middle, that yellow part, or up north in the Pilbara, which is maybe a little bit more water abundant, but still very, very dry. Population growth is placing increasing demands on water supply, but also on food security. And this is where it gets very interesting, because we start seeing now, this is a map that shows the wheat belt of Australia, in this case Australia. This is southwestern Australia, around the Perth area. And this can be the same in Africa, Southern Africa, same in California, same in different parts of the world. Exactly the same process is happening. We are seeing isohyates that are shifting. They're shifting over time as deserts are expanding, and this is caused by a whole lot of factors. Climate change related factors, but also about deforestation, because this area, this southwestern part of Western Australia, is a forested area, and as people live in there or move in that area, they cut down trees. The city expands, suburbs grow, and you start changing the ecological processes. You start changing the evaporative losses, caused by these trees. Rainfall patterns start changing. So the important thing is that those isohyates are shifting. They're shifting from right to left, from east to west, and with that, they're squeezing the population into a narrow strip along the coastal area, and this has got very, very, very important engineering constraints or engineering problems. So these things are dynamic. They are moving, and whether you believe in climate change or not, it doesn't make a difference. Some people don't believe in climate change or anthropogenic cause of climate change. That's beside the point. The fact is they are moving. Who caused it is really immaterial. The fact is that the isohyates are moving. And we see that same thing happening in Southern Africa. There's that 860 millimeter iso height that goes sort of east-west, just north of the border between Namibia and Angola, where the headwaters of the Kunene and the Okavango and other rivers arise. Some of the Zambezi tributaries come from that area as well, and the Kuvulai River also has got its headwaters in that area. Those iso heights are moving northwards. The desert is expanding, and ultimately the source of those waters will be cut off to countries like Namibia, countries like Botswana that will become increasingly arid, also mining-based economies. So similar things between these different countries. Desert areas are expanding for various reasons, and this has serious implications for human settlements in the relatively well-watered parts of Australia. And Perth, as I said, they've got this very, very high quality water utilities corporation, one really, really world-class organization. But these are the challenges, or at least some of the challenges that they're facing, those shifting iso heights. The viability of agriculture is a critical component. So as human populations expand, more pressure on agriculture. But because of human population expansion, your environment is also being impacted, and therefore your ability to grow food is also being squeezed out. And this is very much a global phenomena. We start seeing competition between agriculture and mining. We've got different examples of that in different parts of the world. And these effects are typically amplified in more in the marginal areas of rainfall. Now we get to the real challenge. I spoke earlier on about MAP-MAR, so that last diagram, that last map was about precipitation, that about MAP. This is about the losses to evaporation. So these are your open pan evaporative losses. And if you look at the scale on the right-hand side there, we go all the way up to 4,000 millimeters of open pan evaporation. So we've got areas, look in the northern part of Western Australia, where you've got extremely high open pan evaporation, and that is our engineering problem. The ratio of evaporation loss to rainfall is about 10-1, exceeds the ratio of 10-1 in places. So for every unit of water that you can conserve from or prevent from being lost to evaporation, you've created a multiplier effect. And if we can now start using IT, we can start using intelligent systems, artificial intelligence that's verifiable. We can start creating credits. We can start creating a tradable commodity, a fungible asset that can be traded on a stock exchange, and that can be used to fund infrastructure upgrades in the future. And this is where it gets into a really exciting part of the future of engineering and the convergence of engineering and intelligence systems. This poses strategic challenges for a number of governments and a number of investors and a number of mining houses. Because the question is, how can the mineral wealth of a country be developed to its full potential under these circumstances? Can the Australian economy retain investor confidence in the face of these hydrological realities? And I would like to think that this is one of the challenges that EIT faces in developing a cohort of professional engineers for the future. We've got to think about these kind of issues. How can the social license to operate be guaranteed when bigger and bigger mining operations are coming on stream that demand more and more water in drier and drier areas where First Nation rights are being impacted, and therefore the social license to operate is a factor. How do we manage national food security? Is it relevant in a world of trade? We're currently sitting in a world where there's a global trade war going on, and therefore importation of food, is that going to be affected? And I know in the Middle East they're very concerned about the importation of food. They want to become more nationally self-sufficient in food security. It's not so much an issue in Australia. It is increasingly going to be an issue in Southern Africa. I've done some work some years ago for the British government where we did some modelling, and we showed that in about 2030, about 2040, around about there, we're going to start seeing countries like Botswana, like Namibia, South Africa, and Zimbabwe are no longer going to be able to produce enough food for their own nations. They're going to become importers of food, and therefore the issue of national water security, national food security, and national energy security is going to start changing, and you're going to start seeing the emergence of, for example, Botswana and Mozambique and Angola as countries that are food producers. They've all got better water conditions than the other 4 countries that I mentioned, but they've each got their own internal political problems. In particular, in the case of Mozambique, you've now got this Islamic insurgency that's raising its head, so that poses a risk for this. But nonetheless, the question is national food security relevant? And it's an open question. And now we start asking the interesting stuff. Where does AI and the digitization of the water value chain come in to mitigate the risk associated with the water barrier? And now we start getting into very, very interesting stuff, because with smart systems, with smart digital systems, with smart sensors in systems, where we can make a digital twin of an entire system. For example, the Water Utilities Corporation of Western Australia. If we can digitize that entire system, and we can start looking and modeling for future options, and we can start literally generating water credits that are tradable. This is, I think, where the future is going. So, making some forecasts now about the future of engineering in these kind of economies. The first thing is that open dam storage is limited and becoming increasingly irrelevant in these arid areas. So we've got to start thinking about things other than open dam storage. That's the cutting edge for engineers to start thinking about, start positioning themselves for career development, think about things other than dams. Alternative storage is needed. And one of the best alternative storages here is something that's being actively worked on here in Australia, managed aquifer recharge or aquifer storage and recovery. And there are engineering companies here in Western Australia that are becoming world leaders in this particular thing, this particular technology, because it's not as simple as just processing water and putting it down an aquifer. We know in Cape Town at the moment, there's the Atlantis project that's coming on stream. That's going to take water recovered from sewage, and it's going to recharge the Atlantis aquifer. And there's lots of political pushback around that thing. In the case of Western Australia, they close to where I live, there's a big wastewater treatment works called the Beanie Up Wastewater Treatment Works, where they recover a large amount of water from sewage, and they pump it into the Leederville aquifer. The EIT offices are at Leederville, so literally the aquifer that's here, where that underlies EIT's building. This is where that water is stored, and they bank it. They bank it for 25 years, and that's an important thing. That's an important thing for the future of humanity. The recovery of water from waste is also an emerging technology of strategic relevance, and I use the word strategic because we're talking now about all these persistent chemicals, these endocrine disruptors, these microplastics, all this kind of stuff that poses technical challenges to microfiltration, to UF, to membrane-based technologies, but it also poses an increased risk to public trust, public confidence in the use of that recycled product. We see it happening in Cape Town at the moment, where there's growing pushback against the recovery of water from waste because people don't trust the processes. So that trust deficit is a very important issue. I'm making a statement. And my statement here is that I believe that Perth Water Corporation is becoming a world leader in both of these things, managed aquifer recharge and recovery of water from waste. So what's happening here in the Perth area, I believe will propel Perth Water Corporation into a world leading position, and other water utilities in the rest of the world will start learning from Water Corporation. The science, engineering, and technology skills associated with this single endeavor will become universally relevant in arid areas, and this is an area that I think EIT should start investing into in the future as well, developing the skill sets around that, and that's what I'm talking to EIT leadership about at the moment. And here we have a situation where literally Australian engineers are likely to become world leaders in this technology. So this is an area of expansion. And if we get back into that concept that I introduced at the start of this conversation about a second order resource that will determine the future, EIT is potentially a generator of that second order resource. Water Corporation is a generator of that second order resource. So there's intellectual property involved, and that IP becomes a national asset. It becomes an asset of great value. And I think this is going to literally propel Australia, Western Australia, into a leading center of technology and engineering innovation, and particularly if we can start making a difference around artificial intelligence, the integration of these systems with digital smart learning platforms. Okay, let's start looking at the evaluation now. I'm just going to ask you. I'm going to put out an exercise for you to do in your own time. You can change this as you want to, but just I want you to think as engineers, think that you're responsible for developing a water supply system for a FIFO camp. FIFO camp is a fly in, fly out mining camp. Most of Australia's mines are FIFO run. So in other words, people fly in for a determined period of time, a week, 10 days, whatever, a cycle, and then they fly back home again. So think of this water supply system for a FIFO camp. Select a location for that camp from the two maps that I've shown you early on that give you the precipitation and evaporation numbers, the ISO heights and ISO breadth numbers, and calculate the evaporative loss for your specific site, whatever site you choose. Assume that water supply is from a mine. So assume that the water quality is potable, because there are all kinds of technical things, in mine water. Not all mine water is high quality. In fact, a lot of mine water is very bad quality. But let's assume that the water supply does come from the mine. So you are just asked to develop a solution for the storage of that water. Assume that the workforce of 400 people is present within a camp. So using industry standards, values, calculate the volume water needed per day for that FIFO camp. And now we start getting into the sort of what ifs for the future. Propose a bulk storage system that is appropriate, but using industry standard values. Also calculate the sewage return flow per day. So of that total volume of water that's needed for 400 people, how much of that goes into sewage return flows? And now we start asking questions, assuming that the technology is available and viable. Calculate the multiplier that could be unlocked if water is recovered from waste for reuse elsewhere. So the question is that water that's recovered from waste useful? Does it have economic value? How do we measure that economic value? Does it have social value? Does it have social license to mine value, which might be different from the economic value? Now we start getting into the sort of interesting areas, because if this multiplier is significant in terms of social license to operate, then it changes the way the sustainability strategy is thought about in the future. And that's where your hard engineering now becomes part of that let's call it company policy, company strategy, investor confidence, capital raising, risk mitigation strategy for these large mining corporations. And now you get to the interesting stuff. How would an AI platform be configured to integrate with existing systems? Most mines operate on a SCADA type of system. So most SCADA systems are not smart, but they've got tons of data. So how do you create an AI platform that is capable of capturing the data from a SCADA system, capable of processing that data, giving you real-time information, and then projecting it into the future to start giving predictions of system stability, system needs, and over long periods of time, changes in overall parameters in which that operation is being run. Okay, so now we start reaching the sort of climax of this conversation, we start redefining the problem, and we define the water. We redefine the problem as being that water is a flux that's infinitely renewable, but we manage it as a stock that is only used once and then discarded. So think about that. Water is a flux, but we manage it as a stock. Please think about that. Think about that in a profound way, because that one sentence of a few words has got a lot of implications. And I think from a career development perspective, if you think about water as a flux, but we currently manage it as stock, there's major career opportunities in that space there. As a stock, water is finite, so the water barrier becomes an absolute limitation. But as a flux, water is an infinite resource, so we are able to prosper beyond the water barrier. So the question is, how do we use engineering, and how do we use IT? How do we use smart artificial intelligence to inform decision making about developing the resources, the first order resources, the mineral resources in arid countries where there's not enough water to develop those resources. And this is where we start getting to interesting stuff. The paradigm of scarcity is about water as a stock. So the dynamics are zero sum. Zero sum means my gain is your loss. And a game of tennis is a zero-sum game. If I get the net, the ball over the net enough times, I win, you lose. There can only be one winner, and because of that, it's a highly competitive game. We've got to think about that differently now, because we've got to start converting that into a plus-sum game. The zero-sum game is about I'm going to make my slice of the pie bigger than anyone else's, so it's inherently conflictual. We've got to start thinking about making the pie bigger for everybody, which becomes a plus sum. My gain is your gain. And that's where the management of water as a flux becomes very, very significant in that. And I want you to start thinking about that, getting your head around that. And I think, in my professional opinion, we need to focus our mind on 5 things for the future. First thing is that think of water scarcity as a collision. A collision. Think of a motor car collision on a highway. Think about a train collision. Think about an aircraft collision with a helicopter and a fixed-wing aircraft coming together. They crash together, and it's always catastrophic. So think of water scarcity as a collision between human demand that's growing and diminishing supply on the one hand. So places like Water Corporation in Perth, they've got to constantly expand their water supply, because your human demand is growing, and where do you get that extra water from? Desalination of seawater, recovery water from waste, etc., etc. But think of water scarcity as a collision. And the second thing you need to think about is aridity being about evaporation losses that exceed water supply. So aridity is not about having no water. The aridity is about losses to evaporation exceeding the amount of water that falls into that area through natural precipitation. And therefore, think of it as a ratio, and think of the multiplier of water as a flux, which now becomes an engineering problem that can be solved. Every problem has a solution. Every dilemma doesn't have a solution, because a dilemma is something that is insoluble. So our role as professionals in the water sector is to convert a dilemma into a series of problems, because problems can be solved, dilemmas can't be. And then we've got to start thinking about the development of smart digital platforms with AI and predictive capabilities. And we've got to start thinking about, beyond the digital twin, we've got to start thinking about integrating all sorts of variables with predictive capabilities, smart capabilities, making dumb SCADA systems smart, and making those available across an entire water supply area. So everything that's supplied by Perth Water Utilities Corporation, how can that be digitized, and how can we develop predictive capabilities? And I'm involved in a team in the Middle East that's doing this right now, and it's a very interesting area. And anyone interested in linking up with me, we can just reach out to me. We can talk about it. And then the fourth point I need you to think about is, water is an economic enabler. Without water, you cannot have economic development, because without water, you cannot have investor confidence. So the transition from a paradigm of scarcity to a paradigm of abundance is about sustainability and the social license to operate. So we have to do it if we're going to continue to grow our economies in these arid areas, and these are technical problems that are all soluble. And then finally, the water barrier is about a transition from a linear to a circular economy. Linear economy, where you take 1 unit of water, you use it, you pollute it, you discard it as waste, and you never ever worry about it again, to a circular economy where we start going to a more sustainable reuse, recycling, reduction, reuse, recycle, that kind of thing. But the circular economy, where we go to zero liquid discharge, zero waste kind of economies, huge amount of potential there in the future. And all of this is good news because each problem is solvable. And I'll just quickly tell you something that's happening in the Saudi Arabia at the moment. The Saudis are saying that we must stop thinking about the traditional desalination model for water, because you take the salt out of seawater to produce pure potable water, you discard all of this, the brine as waste, and you now produce water that's got low economic value, because water is something that's very funny, that's got low economic value even in water scarce areas. People don't want to pay for water. So you always got a problem with this, with the social barriers to providing low-cost water. So the business model there is a difficult one, because people reluctantly pay for this water. And so what the Saudis are saying now is we must think differently. We mustn't think about removing the salt from the seawater in order to provide clean drinking water. What we must do is think about how to concentrate salt. How do we concentrate salt in a way that we can get chemically pure products coming out of the line, and a byproduct of that process is potable water that we can then sell as a waste product. So the potable water becomes the byproduct, not the actual intention of the process. And the concentration of salt becomes the actual process. So think about that image I showed you earlier on, about 97% of the water on planet Earth is salt water. We don't have a water problem. That's a water scarcity paradigm. We have a salt problem. We've got to start thinking about how to manage our salt, how to reduce salt, recover, recycle, etc. That's the challenge for the future. That's all the good news. And with that, I'll say thank you very much. This image on the left here, this is acid mine drainage from the Witwatersrand goldfields, where we've now got between 4 and 5 grams of salt per litre of water discharged into rivers. Those rivers are now increasingly polluting the drinking water resources of large parts of South Africa. So here we have literally the reality, the rubber hitting the road, a bite of the reality sandwich, where as a result of more than a century of mining, we've now got saline, acidic, highly acidic salt water going into rivers and causing this mineralization we see on the left-hand side here, and slowly reducing the capacity of those rivers to be used as a resource in the future. So we want to learn the lesson from the Witwatersrand goldfields and apply that now to Western Australia, that we don't have to repeat those mistakes. We can learn from those mistakes. And this is where many, many lessons can be learned, and I'm really thrilled about my opportunity here at EIT, and I'm very grateful that I've got a chance to talk to all of you. The harsh decisions that Australia will be forced to make about developing its mining economy in spite of fundamental water constraints will create a new generation of engineers that will be in global demand in the not too distant future. And I'm very, very grateful for your time, and I thank you very much. And I will now throw it open to Chapiso. You can now moderate going forward.
Thank you so much, Dr. Anthony. A lovely, lovely presentation, and I'm not flattering you. It was amazing indeed. I actually took down some notes, so I'm pretty sure that the people who attended as well have some questions. I have noted down the questions they have. But before we go through the questions, let me just go over a couple of slides, and then I'll be able to tell our viewers today, and you'll be able to actually answer those questions. So guys, if you're interested interested in which courses this topic covers, it's civil engineering, industrial automation, instrumentation and process control, as well as some data comms and industrial IT programs, all which we have at the Engineering Institute of Technology. That is just our upcoming courses that are running from the 3rd of June. There are courses that are running throughout the year. Some of them actually repeat. And then lastly, the certificate of attendance. Please note you can either scan the QR code or use the link. I will provide the link in the chat box as well so that you guys have easy access for it. I'll also pin it down. Now, for the questions, there's some really interesting ones. Let me read them to you, Dr. Anthony, and then you can possibly answer them. I have questions of my own, but because we've gone over time, I'll just read the questions from our attendees today. Nisa is asking a couple of questions. Do you think, okay, this one is from Nelly. Do you think reducing the rate of evaporation will lead to disturbances in cycles such as the rain cycle and the flood cycle, or too much water in parts of the world? That's the first question.
Okay, yeah, that's a great question. Everything has consequences, so there will certainly be consequences. So it becomes a trade-off. What is the most sensible trade-off, that we've got to make? And you can only make a trade-off if you can measure. And if you, that's where the AI systems, that's where these smart systems that I'm talking about comes in. I cannot see a future in the water sector without an integration of very, very smart artificial intelligence systems. I just cannot see it. So it's a manageable problem, but I'm grateful that you've raised it as an issue. But I think the risk can be minimized, and that's essentially what the engineering side is all about. How do we minimize the risk? How do we make it economically viable? How do we make it socially acceptable? That's the important thing. Is a solution socially acceptable, economically viable, technologically capable? Those are the three things that I always use in evaluating any new technologies that come out.
Okay. Now, this question is actually from Lisa. The previous one was from Nelly. In what ways is the changing hydrological cycle creating water security challenges by causing unexpected flooding in dry regions and increasing droughts in areas that used to receive regular rainfall?
Yes, so disturbances are all about deviations from the norm. If you are used to getting water in a certain way, in a certain rainfall pattern, for example, and if you're living in a flood-prone area, then over decades of time, you've built flood control barriers, and therefore you've mitigated the risk that way. Now suddenly your climate starts changing in some way or other, caused by whatever reason, and all of a sudden now your planning is no longer what it used to be. Remember, flooding is an extreme event. It's not only about being inundated with water, it's also about sedimentation. It's about damaging to other infrastructure, sewage lines, bridges, hard infrastructure, harbors, etc. So it's a devastating thing that happens over time. I hope I've answered the question.
Thank you. We have another question from Mohale, and he's asking, can the recovery of water from waste be reliable in terms of water quality for domestic use? Will it not require an upgrade of treatment plants?
Well, that's a great question. In the 1980s, the CSIR in South Africa was involved in the development of a water recovery plant in Windhoek, Namibia. So if you know anyone that lives in Windhoek, Namibia, they've been drinking recycled wastewater since the 1980s. And if you know anyone there that's got two horns on their head and have got any other sort of strange deviations, either cellular or neurological or something of that nature, or cancer forming, etc., I'm not aware of it. But of course, this is the flippant answer, but that's a very real question. It's a very real problem. We're going to have to face that in the future. For example, I cannot see the city of Johannesburg or the Rand water area of supply. I cannot see them continuing with business as usual without doing something about, I think there's something like 32 wastewater treatment works that discharge into their area of supply. So I think they're going to have to start doing something about that. So that's an engineering problem. It's a social problem. But of course, now one of the complexities there is in the case of Perth, where they recover about 120, maybe 150 megalitres of water per day from sewage, where they discharge the brine out to sea. Because they're at the coast, you can't do that in Gauteng, because in Gauteng, you can't just discharge your brine that you're 800 kilometers or 600 kilometers away from the nearest ocean, so you can't build a pipeline over that distance. So it becomes a brine management problem, becomes a social problem. It becomes a trust management problem. But all of these things can be solved, and ultimately, I cannot see a future in Gauteng without doing that. So wherever you go in the world, wherever you see this happening in the world, you're going to have a different set of problems, but they're all going to come down to these, the management of public confidence, public trust, the trust deficit. And where we're likely to see this happening, I think, earlier on in South Africa is probably going to be Cape Town. Cape Town's playing a leading role in this kind of development. And the lessons learned from the Fori water recovery plant in Cape Town, that's going to start teaching the rest of South Africa about how to deal with public perceptions and engineering design problems.
Okay, there we are. We have another question from Gabelo. Gabelo is asking, can groundwater recharge from surface water be an alternative? I.e., he's asking channeling surface water to ground aquifers or boreholes.
Yes, groundwater recharge has been practiced quite widely. In the 1990s, I had the privilege of going up to Botswana when they were busy building the north-south carrier pipeline from the north to the south to the city of Gaborone, and I was proudly shown what appeared to be a dam full of sand. And the chief engineer was very proud of his dam, and I said, but the dam is full of sand. I don't see any water. And he said, the water is between the particles of sand. This is a groundwater recharge project. So it's been widely practiced in Botswana and Namibia for decades already. It's something that we're going to have to do increasingly. However, having said that, there are challenges to it. The one challenge is you've got to have good geology in order to do it. If your underlying geology is not conducive to groundwater recharge, then you cannot do it. So in the Witwatersrand area, in the Gauteng area, where you've got hard granite, basement granite, there's very, very few areas there that are suitable for groundwater recharge. In the case of Perth here, we've got this Leederville aquifer, which is quite a deep aquifer, but it's a confined aquifer. So once the water's pumped into that aquifer, it moves out laterally over a very wide area, but it can be stored for a long period of time without leaking. It doesn't leak out elsewhere. So it all depends on your source of supply on the one hand, and also depends on your on the host geology. So there's never one silver bullet solution. That's the take-home message here. In engineering terms, you'll never find one silver bullet solution that works everywhere universally. You're always going to look at a range of solutions, and the clever engineer is going to come up with the appropriate solution to a correctly defined problem.
Okay, I do believe that was the last question. The rest are just people relaying their thanks for the amazing presentation. Ladies and gentlemen, please note this presentation is going to be shared on our YouTube channel, as well as going to be sent to your email addresses within 24 to 48 hours. I think we all have questions. If you are in the Southern African part, you did hear we have until 2040 to get our water and food sorted, and then we will be in the danger zone. However, thank you so much everyone for attending. I will continue to be online to monitor any questions regarding the certificates of attendance. If you have any other questions, please be sure to leave them on there. We really do appreciate your attendance, and we will see you on the next one. Thank you, Dr. Anthony, and thank you to everyone else. Goodbye.
Pleasure. Thank you very much.